The year is 2025. Beneath the rolling hills of Kentucky, something else was stirring. Deep within the Earth's crust, scientists picked up faint tremors. Not earthquakes, not in the usual sense. These were different. Rhythmic. Almost patterned. A subtle vibration, a geological whisper. Initial data trickled in from seismometers scattered across the state. These instruments listened to Earth's heartbeat. But this signal was unique. It suggested a vast, unknown void, or perhaps an unprecedented geological structure. Something massive, hidden from human eyes for eons. The readings were almost too incredible to believe. Kentucky was about to surprise us all. The scientific community buzzed with cautious excitement. These new signals pointed deeper. They hinted at something primordial, a mystery buried beneath familiar ground. The quest began in earnest. A consortium of geophysicists and geologists assembled. Universities and research institutions pooled resources. The U.S. Geological Survey played a key role. They brought advanced sensing technology. Their mission to map this anomaly, to understand its nature, its depth, its scale. This wasn't just routine fieldwork. There was a palpable sense of impending discovery. The Earth was speaking, and we were finally listening. Teams deployed across central Kentucky. They used an array of sophisticated tools. Seismic reflection surveys were paramount. These send sound waves deep into the Earth. The echoes paint a picture of subterranean layers, like an ultrasound for the planet. Ground-penetrating radar added another dimension. Magnetometers measured subtle magnetic field variations. Gravimeters detected density changes below. Every piece of data was a clue. The data streams flowed into supercomputers. Algorithms worked tirelessly day and night. Slowly, a three-dimensional model began to form. It showed something truly remarkable. Not a simple void, not a uniform structure, but an intricate network of vast chambers, extending for tens, perhaps hundreds of square miles. Confirmation required direct investigation. Models and remote sensing are powerful, but seeing is believing, especially in geology. A plan was hatched for exploratory drilling. A high-tech drill rig, usually for geothermal exploration, was repurposed for this scientific endeavor. The target, the largest chamber indicated by the surveys, a zone calculated to be nearly a mile wide and hundreds of feet high. The anticipation was immense. The drilling commenced in early 2025. It was a slow, meticulous process. Each core sample pulled from the depths was scrutinized with intense interest. First, familiar sedimentary rocks, limestone, shale, then deeper into older, metamorphic layers. The drill bit chewed through gneiss and schist. The team monitored progress around the clock, waiting for the breakthrough they hoped for. Then, it happened. At 16,850 feet, the drill suddenly lost resistance. It had punched through into an open space. Sensors on the drill string relayed data. Atmospheric pressure within the void was stable. Temperature was a surprising 85 degrees Fahrenheit. A specialized camera, encased in hardened steel, was carefully lowered down the borehole. The team gathered around the monitors, holding their collective breath. The first images flickered onto the screen. Gasps filled the control room. It was a landscape of breathtaking alien beauty. Section 4, a subterranean cathedral, the Mammoth Crystal Array revealed. The discovery was officially named the Kentucky Mammoth Crystal Array, KMCA. The initial chamber explored via probe is now called the Thorne Chamber after Dr. Eris Thorne, the lead geophysicist. It alone is estimated to be 0.8 of a mile wide and averages 600 feet in height. But the seismic data suggests it's just one part of a network covering at least 50 square miles. The crystals themselves are primarily selenite, a form of gypsum, but not like any selenite seen before. These are astonishingly pure, almost optically clear, and of a size previously thought impossible. Some individual blades exceed 100 feet in length. Their growth patterns suggest a slow formation over millions, perhaps tens of millions of years. What makes the KMCA truly stunning is their intricate organization. They form colossal geodes and interconnected vaults, creating a subterranean wonderland. Section 5. Rewriting the textbooks: What this means for geology. This discovery beneath Kentucky is profound. It challenges existing geological models for cratonic interiors, the stable cores of continents. The KMCA suggests vast, complex systems can form and remain hidden deep within them for unimaginable lengths of time. The conditions required for such colossal crystal growth are not fully understood yet. It implies a very specific, long-lasting hydrothermal system. The age of the KMCA is a critical question. Preliminary dating suggests the cavities began forming perhaps 250 to 300 million years ago. The crystals themselves may be younger, growing slowly over subsequent geological epochs. This timeline places its origins in a period of significant tectonic stability for the region. The find has immediate implications for our understanding of subsurface hydrology and mineral precipitation on a grand scale. It also forces us to reconsider the potential for similar structures elsewhere in other seemingly stable continental regions. Section 6. Echoes Beyond Kentucky. A new paradigm for discovery. The Kentucky Mammoth Crystal Array isn't just local news, it's a global wake-up call for Earth scientists. It tells us that our planet still holds deep secrets, vast undiscovered realms beneath our very feet. We have mapped the surface of Mars more completely than our own planet's deep subsurface. This discovery shifts that paradigm. It ignites a new era of inner space exploration, a quest to understand the hidden Earth. The methodologies used to find the KMCA, advanced seismic imaging, integrated sensor networks, will now be refined and deployed elsewhere. Geologists will re-examine old seismic data from other parts of the world, looking for subtle signatures previously overlooked. Areas with similar deep geological settings, stable cratons, ancient fault lines, deep aquifers, will become prime candidates for new surveys. The discovery also has implications for resource geology. Though the KMCA itself will be protected for scientific study and preservation, the understanding of how such large mineral concentrations form could guide the search for valuable ore bodies or geothermal energy resources. It refines our models of fluid flow and chemical transport within the Earth's crust. Section 7. The Journey Within. Future Exploration and Enduring Wonder. The immediate future for the KMCA is clear. More research, more exploration, carefully. The first priority is non-invasive study, expanding the network of seismic sensors to map the full extent of the crystal array. Scientists are also planning further robotic missions through the existing borehole and potentially new ones to collect samples and deploy long-term monitoring stations. The challenges are significant. Operating robots in such a deep, complex environment is technically demanding. The crystals, while robust, are also delicate. Preservation is paramount. Any exploration must minimize contamination, especially if there's a chance of discovering unique microbial ecosystems within the array. The ethical considerations are being carefully weighed. This is a pristine, ancient environment. Many questions burn brightly. How did this colossal system form with such purity? What is the exact source of the minerals? Are there active geochemical processes still ongoing? And the biggest question of all, is there life?